Today we're going to be looking at 5 binomial distributions. So for many probability experiments, the results of each trial can be reduced to 2 outcomes, success and failure. This type of experiment is called a binomial experiment. For example, when a basketball player attempts a free throw, he or she either makes the basket or does not. You have success, making the basket, failure, missing the basket. So we have a couple of characteristics about a binomial experiment that we have to make sure our experiment follows. The first one is that the experiment has a fixed number of trials, where each trial is independent of other trials. So remember, our most common time that we see something being dependent is when we are drawing a card and not replacing it, or picking something out of a drawer but not replacing it. Okay, that key thing, not replacing. Our second characteristic, there are only 2 possible outcomes for each trial. And those 2 outcomes are success and failure. So making a basket, not making a basket. Drawing a 2, not drawing a 2. Okay. Our third characteristic is that the probability of success is the same number for each trial, which should hold true with the fact that we have independent trials. Okay, our fourth characteristic is that the random variable x represents the number of successful trials. The number of successful trials. So we have some new variables that we're going to bring in for binomial experiments and some notation. So the first one, the number of times a trial is repeated, is going to be n, our sample size. The probability of success in a single trial is going to be lowercase p. The probability of failure in a single trial is lowercase q. And we find q by finding the complement of p. So q equals 1 minus p. And then the number of successes in n trials, we already said was going to be the random variable x. So for this first 2 examples, we're going to just decide whether the experiment is a binomial experiment. If it is, specify the values of n, p, q, and x, and if not, list y. So a jar consists of 4 red marbles, 3 green marbles, and 7 blue marbles. You randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. So first thing we need to decide, is it going to be a binomial experiment? So do we have a fixed number of trials? And we do, because we're selecting 3 marbles. Are each of those trials independent from each other? And they're not, because we're not replacing, which automatically means this is not a binomial experiment. because each trial is not independent by not replacing the marble. Okay, our second example, you take a multiple choice quiz that consists of 4 questions. Each question has 4 possible answers, only one of which is correct. To complete the quiz, you randomly guess the answer to each question. The random variable represents the number of correct answers. So, we have a fixed number of trials because we have 4 questions. The probability of getting question 1 correct does not change the probability of getting question 2 to correct. Everything is independent. There's 2 possible outcomes. You either get the question correct or not. Probability of success is the same for each trial, 1 out of 4. And our random variable x represents the number of successful trials. So we've met all 4 of our criteria. So yes, it is binomial. So now we need to state what n, p, q, and x are. So n, we already said, is 4. It's the number of questions. P, our probability of success. So there's 4 possible answers, only one of which is correct. So it means our probability of success is 1 out of 4, or 0.25. Our probability of failure is 1 minus p, or 1/4, which is 3/4, which would be 0.75. Then, to list our random variable, we're going to list how many correct answers could we get. So we could get none correct, 1, 2, 3, or all 4. Your x values will always start at 0 and will always end at your n. All right, once we know that we have a binomial experiment, we can find the probability of x successes and n trials using a formula. The probability of x equals n cx, which is a combination. I'll show you how to plug it in your calculator in a second, times p to the x power times q to the n minus x power. Okay, the easiest way to kind of remember this formula in regards to the second part here is we have the p is our probability of success, so our exponent represents the number of successes. Actually, let's do for the exponent. Our exponent on our q is the number of failures. Sometimes thinking about it like that helps remember the formula. I will give it to you, but it helps make sense of it. Okay, so this first part is NCX. It's a combination, and we're going to plug that into our calculator. And the way we do that is we hit math. You're going to hit the right arrow over until you see PROB, probability. And then you're going to click on number 3, which is that NCR. Now, if you have a TI-83 calculator, you'll have to type your N in before you do these steps. The majority of you have a TI-84, so you should be fine. Okay, so we're going to do another problem, and then we'll practice plugging in the calculator. So using the binomial probability formula, find the probability that you get exactly 4 questions correct on a 6-question multiple choice quiz. Each question has 3 possible answers, only one of which is correct. So N, how many questions do we have? And we have 6. The probability of getting a question correct, it says that we have 3 possible answers. So it's going to be 1 out of 3. And Q is going to then be 2/3. Now, on these two probabilities, we don't want to round, so we're just going to leave them as a fraction. Okay, we want to know exactly 4 questions correct, so that means our x is going to equal 4. So the probability of 4 equals, so NCX, so we started off with 6 questions. Of those 6 questions, we want to get 4 correct, times the probability of success is 1/3, and we want to get 4 of those successes, times 2/3, and you can either do 6 minus 4, based off of the formula that's listed above, or if you'd rather just write a 2 here, that's fine as well. I do not care which way you do it. All right, so now we're going to type this whole thing in the calculator. If I can find my calculator app. All right, so when we type this in, going to math, going over to probability and clicking on number 3, and then we can type in the 6, right arrow over to the 4. Hit your right arrow to move it back up to the top, times the quantity of 1/3 to the 4th power, right arrow out of our exponent, times the quantity of 2/3 raised to the 2nd power. Okay, remember probability, we're going to round to the nearest 3 decimal places, so we're going to have 0.082. Okay, trying our next one. A card is selected from a standard deck of cards and is replaced. This experiment is repeated a total of 5 times. Find the probability of selecting exactly 2 clubs. So our N, number of trials, is 5. Our probability of getting a club is 1 of the 4 suits. Our probability of not selecting a club is 3 out of 4. And we want to find the probability of exactly 2. So the probability of 2. All right, plugging in our formula. So we have 5 trials. Combination of those 5 trials, we want to get 2 successes, times 1/4, the probability of success that we want to happen twice, times the probability of failure, 3/4, which we want to happen 5 minus 2 times, or 3. All right, try plugging that into your calculator. And you should get approximately 0.264. Okay, we're going to combine what we did last class with this, and we can now construct binomial probability distributions, which is what we're going to do on this next example. When you have a binomial probability distribution, it helps when you're trying to find multiple probabilities to go a little faster. So I'm going to show you a couple different ways we can do this. So in a survey, United States adults were asked to identify which social media platform they use. The results show that 62% use Facebook. 6 adults who participated in the survey are randomly selected and asked whether they use Facebook. Construct a binomial probability distribution for the number of adults who responded yes. So identify N, P, Q, and X first. So our N, we selected 6 adults. Our probability that they said yes was 0.62, or that 62%. Q, the complement, so 1 minus 0.62, which gives us 0.38. And then we're going to list our X values. So remember, we start at 0, and we list all the way up to N. Yes, you do need to actually list them. If you just write 0 to 6, I'm not going to give you credit for that. All right, remember our binomial or our distribution tables. We have our X and we have our probability. So our X's are just going to be the ones we just listed. So 0, 1, 2, 3, 4, 5, and 6. And then we're going to plug in what we know into our binomial probability formula. So our N is 6, combination 0, times 0.62 to the 0 power, times 0.38 to the 6th power. All right, so let's plug that in our calculator. So we have 6 combination. Oops, helps if I type it in correctly. Let's try that again. All right, so 6 combination 0 times 0.62 to the 0 power, because we want 0 successes, times 0.38 to the 6th power, because we want 6 failures. So rounding that to the nearest thousandth, we get 0.003. Okay, so I'm going to show you a shortcut rather than having to type that out over and over and over again. If you hit the up arrow on a TI-84, it'll highlight your previous typing, and if you hit enter, it'll copy and paste it down. If you have a TI-84 that's older or a TI-83, if you hit the blue button second and then you hit enter, it'll also copy paste it down. So it just kind of depends on your calculator what you need to do. So looking at our formula, we're going to now change these exponents. So our 0 is going to become a 1. Our 0 becomes a 1. And we had 6 trials. Of those 6 trials, 1 is a success, which leaves 5 to be a failure. And now we have our new probability of 0.029. Okay, pause the video, take a couple minutes, try to fill in the rest of the table, and see what you get. Okay, now that we have a completed table, remember our 2 characteristics of a probability distribution table. Let's check them. Our first one was that each of our probabilities are between 0 and 1, which they are. And our second characteristic of a probability distribution table is that the summation of our probabilities should also equal 1. Okay, if we add up all of our probabilities, that checks. So we're good to move forward. Okay, now that we have this table, we're then able to answer some questions. So, from the previous example, if we want to find the probability that exactly 2 responded yes, we already know that our answer is 0.120 from our table when x equaled 2, our probability is listed. So, knowing that, let's look at a couple others. If we want to find that the probability is at least 2, so the probability that x is greater than or equal to 2, you have a couple options of what you can do. You can add 2 plus 3 plus the probability of 4 plus the probability of 5 plus the probability of 6. Add those all up. If you do that, you should get 0.968. The other thing you could do, this one wasn't so bad because our n was 6, but if our n was 20, we would be adding for a while. So we can also use the complement. Which is like the backwards. So the probability that x is greater than or equal to 2 would be 1 minus, okay, so instead of being greater than, we have to be less than, and we were equal, so we're going to take off the equal. So we could also do 1 minus the probability that x is less than 2. To be less than 2, that's the probability of 0 plus the probability of 1. So looking back at our table, if we take the probability of 0 and the probability of 1 and add them together, we get 0.032. If we subtract that from 1, we get 0.968. Depending on your table and what your n value is, sometimes it is faster to use a complement, but sometimes it's also harder to think about. All right, third example, fewer than 2 responses of yes, we already found this. The probability that x is less than 2, we said was 0.032. All right, 2 more concepts. So I talked about being able to use the binomial probability formula, making our table with that, but I also said there was going to be another way to find our probabilities. So you have a packet of tables, and we can find the probability from this packet if our p-value is one of the probabilities listed. So we're going to set up this problem first, and then we're going to look at the table. So about 10% of workers 16 years and over in the United States commute to their jobs by carpooling. You randomly select 8 workers. What is the probability that exactly 4 of them carpool to work? Use a table. So we know about 10% carpool. That is our probability of success. We are randomly selecting 8 workers. So that means n is going to be 8. We want to know when exactly 4 of them, how many or what's the probability that exactly 4 are going to carpool. So to find the probability of 4 using our table, I'm going to switch over here. Actually, where do I have it? All right, so we have a binomial distribution table. Looking on your left, you have your n's and you have your x's. Notice if you have n as 2, you have x 0, 1, and 2. Across the top, you have your p, your probability of successes, going from 0.01, 0.05, and then going up in increments of 500ths. So the problem we were just looking at, we're looking for when n equals 8. So I'm going to scroll down here. And we are looking for when n equals 8. We're looking for when p is 0.1, which I believe is this third column. And we want to know when x is 4. So our answer is going to be 0.005. So our answer, 0.005. No extra work, just looking at the table, pulling the answer from it. Now, this only works if you have a probability that exists on that table. I guarantee you will have one of each type moving forward. Okay? You'll be expected to use the formula, and then you'll be able to use the table if you choose. Okay, couple of last little things. Graphing a binomial distribution, it's a discrete probability distribution, so you can use the same process by graphing a histogram. And then mean, variance, and standard deviation, you can use the same formulas as what we did in 2-4. Or with a binomial distribution, we have some shortcuts. Our mean, we can use the formula mu equals n times p. Our variance, remember, is sigma squared, is going to equal n times p times q. And our standard deviation is our variance with a square root. So the square root of npq. And remember, when we do this, we want to look at the unrounded. Unrounded. All right, so we're going to do one example of this. In Pittsburgh, Pennsylvania, about 56% of the days in a year are cloudy. Find the mean, the variance, and standard deviation for the number of cloudy days during the month of June. Interpret the results and determine any unusual values. So P, our probability of success, is going to be 0.56. Take the complement of that, subtracting from 1, we get 0.44. And this one, our n, we have to think a little bit. It says that we're looking for the number of cloudy days during the month of June. There are 30 days in June. All right, so first thing, finding our mean. Mu equals n times p. So we have 30 times 0.56, which when we multiply those, we get 16.8. Our variance, so sigma squared, equals n times p times q. So 30 times 0.56 times 0.44 is going to be approximately, if we round to the nearest tenth, we get 7.4. And then our standard deviation is the square root of npq. If we look at our variance unrounded, we have 7.392, which if we round to the nearest tenth, gives us 2.7. Okay, so our mean, our variance, and our standard deviation, other than the fact that it's a new formula, are easier to find when you have a binomial distribution table than a probability distribution table where we had to multiply our columns together.